Thank you for the kind introduction. It's a pleasure to be here. I hope you can all hear me. I'll try to project. And as you've probably guessed, this talk will be, I'll start very generally about a topic you've probably heard maybe too much about, quantum computing. Well, bear with me, you'll hear a little more. I'll try to manage the hype and couch it in some realism. But indeed, I'm working with the platform that's arguably the best candidate to actually scale and build a useful quantum computer. And it remains to be seen what useful means, because we still, what I lose sleep at night over is that we still don't know what these things are good for. But we're going to build them, and if history is any guide, that's actually a pretty good start. If we have a new technology, let's build it and see what it can do. We may only learn after we build, and that's definitely what happened with classical computers. So as you can guess, this is a picture. It's not live, but it's a few-minute video on infinite loop of exactly 25 atoms. These are charged atoms. They're atomic ions, and they're held in an electromagnetic trap in a vacuum chamber. The reason they're glowing is we're shining laser light on them and collecting the light, the fluorescence. The atoms are separated by about 5 microns or so, and we can obviously resolve each atom. Each atom is actually very cold and about 1,000 times smaller than these blobs. The blobs are just diffraction-limited spots from our optics. How do we know they're very cold? Well, I'll tell you a little bit about that later. But this turns out to be, like I said, a very attractive candidate to do many-body quantum physics, make entangled states, build a quantum computer. And the reason, there's some very fundamental reasons. Well, when we turn the laser light off, the atoms are still there, but they're nearly perfectly isolated from the environment. They're not part of a solid. They're not on a surface. They're in a vacuum. There's not even really much air around to bump into them. And there's no light that these individual atoms will respond to because they're atoms. They only see very narrow bands of light. They strongly interact with each other as well, so we can have a natural way to wire them together. And as I'll show you, we can measure them and initialize them with very high fidelity. So these are all the requirements to build a quantum computer, and they're very hard to do all together. You need coherence when left alone, and then you need to be able to measure, pull out the information in a quantum system with very high efficiency. And these trapped ions have all that. So I'm going to start for a few minutes at a very, very high level of quantum computing, introducing it from concepts maybe we're familiar with. Now, in this audience, we're familiar at least with the concepts of quantum mechanics, quantum physics. Typically, for a broader audience, that's maybe the foreign element here. But for us, the foreign element might be information theory itself. And I'll remind you that in the 20th century, these two luminaries really brought the theory of information to light. And the reason I'm highlighting their contributions is that they made abstract theories about information that prefaced the introduction of technologies based on bits and based on making abstract machines. Alan Turing, you've probably heard of the concept of a Turing machine. I don't have a laser pointer, but I'll use the old-fashioned. I like these better. So a Turing machine, nobody really builds these things, but in an abstract way, if you had a tape full of bits, zeros and ones, and you can move the tape across a head that has memory, and maybe you can do operations, logical operations between the memory and the tape, you can do an arbitrary computation. Turing showed that mathematically, all classical computers can be mapped to that abstract model. And Shannon, for his part, published a wonderful paper, a very long one, I think it was in 1949 or 50 or something like this, on the theory of information. In there, he defined the bit, essentially, as the fundamental unit of information, and this thing called the Shannon entropy, which as students of thermodynamics and stat mech, we recognize the connection to thermodynamic entropy. But the idea is if you have an alphabet with K symbols with probabilities here, the amount of information content in a given letter of that alphabet is given by this formula. So bits. Bits can be zeros or ones, of course, and with these two abstract ideas in information theory, it really seeded the 20th century information era, the search for bits in nature to build devices that we can use to compute. And we all know the history of that. In the middle of the 20th century, there were vacuum tubes that they worked okay. And these vacuum tubes are the backbone for the British Colossus computer, ENIAC in the US, and MESM in Soviet Union, that pieced together thousands of vacuum tubes to do computations. And so the vacuum tube is a particular realization of a bit. Without getting into the physics of the vacuum tube, it was, as we all know, replaced by a much more reliable technology, even though this picture doesn't look very reliable. Physicists love this picture because this doesn't look like a transistor, it looks like a physics experiment. And it's basically a sheet of germanium here with a gold contact here. There are 3 terminals, 1, 2, and 3. And this is a transistor, an electronic transistor. And the reason this is interesting is it's solid state. There's no more vacuum tubes. And vacuum tubes turned out to be not very reliable. They broke a lot. Well, this particular device breaks all the time, not reliable. But because it's solid state, there was, of course, the potential of miniaturizing it. And we all know the history of that over the last many decades. I express it in terms of Moore's law, the ability to shrink transistors by about an order of magnitude every decade or so, or a factor of 2 every couple of years. And this is just the last few decades of Moore's law relative to, I guess, the transistor density in 1980, or 1978, sorry. And this is exponential growth, of course. And it's showing signs of saturation, and I want to dwell on that a little bit. And the reason it's showing signs of saturation is that we know the latest processors have transistors that are, I don't know, 10 nanometers across. And when you make transistors smaller than that, there are issues actually involving quantum mechanics. You start to see noise in these systems. Very difficult to do lithography at that level. So one of the overhyped statements of quantum computing is that it will allow us to get back on Moore's law. That's a little silly. Quantum computers are completely different than any computer represented on this Moore's law plot. But I put the Moore's law plot because of what Richard Feynman said about solid-state electronics back a long time ago, 1959. This is even before Moore's law kind of started going, but he gave a lecture at the American Physical Society meeting that year. And there's this essay, you may have heard of it, there's plenty of room at the bottom, meaning that solid-state devices are amazing because you could imagine shrinking them down to individual atomic scale. And there's lots of zingers in this article. It's only a few pages. You can look it up and read it. I recommend you do that. But he says when you get down to circuits of a few atoms, there are completely new opportunities for design. And the reason there are completely new opportunities for design is that at that level, the laws of nature kind of change. They're different. The laws of nature are quantum physics and not the macroscopic physics of F equals ma. Now, Feynman and everybody else at the time didn't know what that opportunity would be. But again, he's a visionary, and he foresaw that there would be opportunities. And I guess part of the ore in quantum computing is that it is a huge opportunity to do something totally different in computing based on these new laws. Another Moore's law, just to show how popular this field has been over the last few decades, is the Moore's law of publication. And so this is actually still a little outdated. I should update this slide. But the number of articles that had these phrases, quantum information, quantum computing, or quantum communication, it's been growing steadily over the years. There's lots of there's over 15,000 papers per year on this field right now. That's quite a bit. I pulled out a slide that I sometimes show also what's going on in this field, why quantum computing and quantum entanglement are very interesting. And it's based on a paper that was little known at the time by John Bell. And he basically continued along the lines that Einstein, Podolsky, and Rosen first pointed out in the 30s, showing that entanglement is strange, it's weird, and it means quantum mechanics is probably wrong. That was EPR's conclusion. And his paper in 1964 was barely cited, but these are the citations to that paper over the time, plotted on a log plot here. We can see there's exponential interest in Bell's inequality, as it's known. And largely this is due to the turn-on of quantum computing that really, in the mid-90s, became very popular, and I'll tell you exactly why that is. We sort of, as a community, we were able to identify the opportunity of quantum. And I'm delighted to speak at a place where Rosen was such an important figure here, and obviously this auditorium is named after him, and there he is. Okay, so quantum computing is based on not bits, but what we call qubits, quantum bits. And as you can imagine, instead of just being 0 or 1, they can be in a superposition, a quantum superposition of 0 and 1 with arbitrary weightings. Okay? So they have a flavor of analog computing in them because the weighting, the continuous variable weighting of a qubit, it can take on any value. So that can be bad and good. And so the way I like to think about this topic is a quantum computer follows a good news, bad news, good news story. So there's some drama here. Well, first the good news. And this is, well, it might be obvious and trivial when you think about it, but when you have lots of qubits, the number of states you can represent in superposition grows exponentially. Right? With 3 qubits, there are 8 numbers we can store with these continuous, we call them amplitudes, the weightings, they're complex numbers. And we can sort of get this massively parallel storage capacity. Now, 3 qubits isn't very much, but if you put many hundreds of qubits together, that is a lot. 2 to the 300 power. 2 to the power of 300 is more than the number of particles in the universe. I know that sounds overhyped, but it's a fact. The universe doesn't contain more particles than that. So even if every particle in the universe is part of a regular computer, it cannot deal with that amount of data. Now, that's not to say that a quantum system can process in a usable way that amount of data, but a quantum state can have 2 to the 300 independent numbers in it. Okay? So that is not hype, that's just a plain fact. We don't exactly know what to do with it. Why? Because the bad news. Okay, so this is a little block diagram. If you were to do a parallel computation on 3 qubits, you get to make 8 calculations at the same time. You get to calculate, say, the square root of x for all the inputs at the same time. Parallel computing. The bad news, of course, is that in quantum mechanics we have this other rule that it's not wave mechanics, but it's the measurement that collapses superpositions to definite values with associated probabilities. In some sense, well, to me, this is the weird part of quantum mechanics. It's the measurement. The wave part is not so weird. It's just it's unitary, reversible. It's given by a wave equation. But the weird part about the measurement problem is that, of course, we can't relate it to the wave part. Maybe there's some controversy there. But in any case, when you measure a quantum superposition, it assumes, it collapses, if you will, to a particular value. And if you're doing this parallel computation and you measure the output, you can't experience all of the outputs at the same time because you're not quantum. You get 1, and it has a probability associated with the weighting of, in this case, 5, or f of 5. So that's no good because it's noisy. If we repeat this experiment again and again, if we have a 1-to-1 function, it's just going to be noise. So no opportunity there, and that's the bad news. Well, in the mid-90s, maybe late 80s even, David Deutsch showed the hint of an opportunity. And he proposed that instead of measuring these quantum bits, we allow them to interfere like any wave phenomenon will. And through that interference, there can be, in principle, applications where the final state of the quantum system before measurement is not a superposition, but a single state, or a few states, but not 2 to the 300 of them. If that's the case, we're lost. But if you can somehow bump the quantum state so that you get this massive destructive interference, then something's interesting. Because when you make a measurement, there's no longer all that entropy, and the measurement becomes a little more deterministic. There's still, in practice, there's probabilities, but if you repeat it a few times, you're going to get the answer. And that answer can, for some very clever algorithms, that answer can depend on all these inputs. That's the opportunity. That's what quantum computers have promised to be able to do. Now, what's going on here? This is very hard to depict graphically, but these red dots, sometimes we call them quantum gates. They bump the quantum state around, just like classical computers bump classical information around using a NAND gate, for instance. There are universal families of logic gates. I won't get into that too much. But a lot of the language from classical computing comes over to quantum, except instead of a NAND gate, by wiring two transistors together, we have something like a controlled NOT gate. That's a popular one. There are many families of quantum gates that work. You just need to be able to span the entire Hilbert space, and there's a lot of theory behind that. Quantum information theory, it's a whole new branch of information theory. So this is very interesting, and David Deutsch himself and a few others showed how to use this in some very demonstration-like algorithms. There were really parlor trick algorithms that you could show that a quantum computer could do something that you couldn't do otherwise, like playing the game of 20 questions. 2 to the 20th is about 1 million. So if you pick from 1 out of 1 million thoughts and somebody asks you 20 yes or no questions, they can usually guess what you were thinking. Well, the quantum version of that is you can guess the information with only one query because you're, in a sense, the cheat is that you're sort of asking 20 questions all in parallel, but you're only asking the oracle, the person or the object that has the information, you're only probing it once. And that's something you can't do classically, but it's not all that interesting because you programmed it with the answer that you know, so you're not really gaining information that you didn't. But it's a demonstration in an information theoretic sense of something new. Now, I mentioned the mid-90s was when quantum computing really went to the mainstream, and it wasn't because of David Deutsch, actually. It was because of Peter Shor. He showed that if a quantum computer were built, it would be able to factor large numbers, exponentially faster than any known classical algorithm. And so many of you know factoring, well, factoring for small numbers we've memorized, but for big numbers it's a hard problem. Every time you add a digit, it gets twice as hard. It's something like that. And the reason it's important, of course, is that the inability to factorize huge numbers is the basis of security in all of our public key encryption systems. So this is a big deal. Now, as I'll maybe talk a little later, factoring is among the hardest problems you could imagine because to factor an interesting number requires thousands of bits, thousands of digits, say a 2,000 digit number. Well, you need 10,000 bits just to represent it. You need overhead, you need to do error correction. A quantum computer to factorize an interesting number probably won't be here for a number of decades. It's very hard to predict when things are decades away. But it's a very challenging problem. You probably need millions of qubits. You probably need trillions of coherent gate operations, and we're not even close. The state of the art now is a few dozen qubits, a few hundred operations, okay? So we need many orders of magnitude to do that. That doesn't mean that there aren't other applications, and I want to briefly touch on those. So how does quantum factoring work? Well, I'm not going to go through the math. This is going to be embarrassingly silly. But the way you factor a number is you store a superposition of all the numbers up to the number you want to factor. Let's say we want to factor 39. So this would require at least 6 bits, I guess. And we store a quantum superposition with the weightings of all these numbers. And you massage the quantum state with a prescribed number of gates that's not exponential in the inputs. So Shor showed that it's a polynomial number of gates that you need. And when you do that, what happens? Boom. The quantum state evolves to a superposition of these two states in binary. And then when you measure them, you get one of the factors. Okay, that's a very hand-wavy, I mean, it's not even a description of the Shor algorithm, but it's a few lines of math. Well, maybe it's a few hours of lecture. Anyway, if you like quantum mechanics and number theory, you should read his paper. It's really cool. Okay. So factoring is pretty out there, and we're not going to be doing it for any time soon. However, there are many other problems that we can't solve classically. They're really hard classically. Problems that are not one-to-one, I mean, a one-to-one problem, I just said, is bad. You're not going to be computing one-to-one functions very well with a quantum computer. But you're going to be computing functions where the output depends on all the inputs, or lots of them. Well, there are a class of problems, I generally would call them optimization problems, that can be really hard. This one's not that hard. What's the tallest peak in this range? Well, you can just see it. Actually, I think it's that one. It depends on our perspective. It's certainly one of these two. But the reason this is easy, of course, is that we only have two variables, x and y, longitude and latitude. And you can plot that and just look at it. Well, if you have a function, a spiky function or whatever, a nonlinear function with, say, 1,000 variables, that's really hard. You have to sort of guess. I mean, you can't plot it, obviously. So there are lots of heuristics that allow us to do those search problems, but they're not very efficient. And you can't prove that you optimized it if you want to maximize a function or minimize a function. So optimization problems are all around us, and we tend to ignore them in culture because we can't solve them. So a good example actually comes from chemistry and physics, and that is like this molecule here. It's caffeine, right? I should know that. So this molecule has like about 100 electrons. Now the electrons, in a sense, they minimize their energy. They orient themselves, just like in water, the two hydrogen atoms are at a 105-degree angle. That actually minimizes the energy. It's a very complicated calculation, even for water. It's not too bad for water, but for caffeine, it's ridiculous. You can't do it. There's 100 electrons, 100 factorial combinations. So this is huge, and classical computers can't solve the ground state of the caffeine molecule. Now, knowing the ground state of a molecule actually impacts how it reacts with other molecules. So it's very important if you're a big pharma company and you want to design catalyzers, or an energy company, you want to make better, better grade gasoline or something. I'm on thin ice on those topics. I don't know much about them, but I do know that electronic configurations, as we know, are very hard to calculate from first principles. They're fermions, and their exchange interaction makes it really hard. Much less molecules like this. This is a nitrogenase. It fixes nitrogen, breaks up N2 into ammonia. Very important for making fertilizer. And you've probably heard the story. I didn't believe it when I first heard it, that 3 or 4% of the world's energy goes into a process that breaks nitrogen into ammonia by the Haber process. High temperature, high pressure, lots of energy. It's a very wasteful process, whereas we know that bacteria can do this at room temperature. And what's thought to be the center of that process is something involving these iron, and in this case molybdenum, heavy metals in these metallic organic structures. And again, calculating the ground structure of this molecule is ridiculous. Now this is probably as hard as factoring a number right now. So we can't think about doing that molecule yet, but I think we should do something like water first, and then methane, and then kind of work our way up. Another type of optimization problem, or another class of optimization problem comes from logistics. You all know the traveling salesman problem. It's one of these combinatorial hard problems. What's the shortest path between a bunch of cities, visiting each city once? Of course, relevant to all kinds of parts of the economy. And we know classically this is an NP hard problem. In fact, actually, quantum mechanically, nobody believes we'll be able to solve this problem exactly using a quantum computer. But quantum computers might be an added heuristic that allows you to at least try to minimize this. If you can map this problem to a cost function and map it to a Hamiltonian and minimize it somehow using gates, there's techniques to do that. Maybe you can do better than a classical computer. You don't have to prove that you're going to do better than a classical computer. Just do it. That's what a heuristic is. It lacks a proof. And so these are very important classes of problems that, okay, you might argue it's unlikely they're going to all hit pay dirt. That may be true, but their impact is more than outweighed by 1 over the probability of doing it. Okay, so I want to switch over and maybe talk a little bit about why don't we have quantum computers right now? What's it take? Well, one observation, I steal this from my colleague Bill Phillips at Maryland and NIST, who's fond of saying that a quantum computer differs more than our classical computers than that classical computer differs from an abacus. And what he means here is that these are both Turing machines. One's a lot more useful and faster, course, but they compute using the same very high-level rules. This is not a Turing machine. And so to me, the corollary here is, well, why should a quantum computer look anything like, certainly not an abacus, actually maybe it'll look more like an abacus. Why would it look anything like a silicon processor that we have now, if it's so fundamentally different? And so to build a quantum computer, I hinted at the beginning, it requires some pretty exotic hardware. Hardware that can be almost perfectly isolated from the environment, yet when you want to measure it, you can do that. So there are a few interesting technologies, and I borrowed this graphic from Science magazine a few years ago. The editors wrote a review of the field, and even since 2016, I added two more columns of interesting technologies. So these are all technologies where we can isolate a certain quantum degree of freedom and do things with it. From atomic physics, we have atoms, we have trapped ions, individual photons. In condensed matter physics, we have interesting dopants in solid state, like the NV, nitrogen vacancy in diamond, a very clean type of defect. There are spins in silicon, superconducting loops, and this is a little bit more theoretical, but the idea of storing information in the topology of a quantum state in a system. Now, of these technologies, I would say these first two are the only ones right now that are being built into systems. Now, as a physicist, it took me a while to learn what that word means, system. What is a system? Well, if you know what systems, well, I don't even know what systems engineering is, really. It's a very vague thing. You know it when you see it, you know it when you do it. A system is something that, let me define it very loosely. A system is something when you build the device, a third party can use it without knowing anything about that device. A good example is your smartphone, right? The reason it's useful is exactly that we don't have to know what's inside. And so these quantum systems are sufficiently stable that we can build systems and software on top of them so that users can play around. And it's no surprise that these two technologies are really the ones that industry out there, big and small, are investing a lot in, with a couple of exceptions over here. I think there are some stalwart silicon companies that aren't willing to admit that silicon probably won't allow us to build big quantum computers. And other ones that I'm not sure they even care about hardware. They're software companies, so they're doing excellent physics at Microsoft. It's physics, really. It remains to be seen whether topological qubits can even be made and used and controlled. Okay, so I'm obviously going to talk about trapped atomic ions. That's what I've been working in. And even trapped atomic ions is a little bit out of the mainstream because it's not solid state. So you have behemoths like Google and IBM that have gone into the superconducting architecture because at least it's solid state. It's pretty exotic solid state. It's cold. And you have to build superconducting loops and connect them in certain ways. But trapped ions, this is from atomic physics. It's a system, it's a quantum system that really hasn't been engineered yet. So this is sort of why I'm very confident in this technology, because there's a lot of engineering to do. And engineering, every step is kind of well defined. It doesn't mean it's easy. It doesn't mean it will be, in the long term, the solution. But there are no physics breakthroughs needed in this technology. That's important. I would say it's really the only technology up here where we don't need breakthroughs. We have ideas on architectures and scaling that do not exist in these other systems. Okay, here's a collection of exactly 80 atoms. They're trapped. Actually, we do use silicon. This is a silicon chip trap made by Sandia, but there's nothing quantum about it. This is just a bunch of electrodes. You can't see them, but there's 100 electrodes here. Think of them as train tracks, electric train tracks to support these ions. These ions actually occupy a space of less than a millimeter. They float above this little bow tie here, about 1/10 of a millimeter altitude above. We focus laser beams across them to control them. So how do we store quantum information in something like this? A couple of atomic physics charts here. Now, we're using, the atom we use is the 171 isotope of ytterbium plus. And the reason is, well, you'll be surprised at the reason, the main reason, but one of them is that it's a very simple atom. Ytterbium plus has only one outer electron. The other electrons are in closed shells. They're frozen out. We never really excite them. There are some details I can tell you later. It's not so important here, but it's almost all this single electron. So it's a lot like hydrogen. In fact, more than you think, because the nucleus of this atom, as heavy as it is, has spin 1/2. So the quantum numbers are exactly that of hydrogen. So the ground state, S, just like in Quantum 101, think hydrogen. The only difference is that the frequency splitting, this is the hyperfine splitting between the 1,0 state and the 0,0 state, is 12.6 gigahertz instead of 1 point something gigahertz in hydrogen. Now, this is a very good atomic clock, in fact, because these two levels are relatively insensitive to magnetic field noise. They have no Zeeman shift to first order near zero field. So I could write a few more digits if I wanted. And of course, when we make more than one atom, it's going to have the exact same properties. It's an atom. That's the beauty of this type of an architecture. It's based on qubits that are given to us by God, right? They're not man-made, so they're not going to be different. Okay, so we're going to store our qubit. Sometimes I label them by spin. It's an effective spin, up and down, 1 and 0, whatever you want to call it. Now, this qubit, we can also, like in most atomic experiments, we can detect the state of the qubit with very high efficiency. And this is afforded by coupling to the first excited electronic state. In the case of ytterbium, it's in the near UV, 369 nanometers. I could write another 6 digits, but that's boring. We have to tune the laser to within a few megahertz of the resonance. And it scatters light very efficiently because it can only come back down. Actually, it could go to these states, but we clean that up very easily. I'm not drawing those levels. It's a so-called cyclic or cycling transition. Okay? It's a 20 megahertz line, so we basically can scatter 100 million photons per second from a single atom. And even if we only detect a small fraction of that light, it's a huge signal. So this is data from a single atom prepared in spin-up and detected. With a window of 50 microseconds, we get roughly 1 photon per microsecond. So we get 30 or 40 clicks. We repeat the experiment many times, so we get a distribution, a roughly Poissonian distribution. Now, the point here is that if we're in the other state, the atom is transparent to this light. It's dark. Because we're 12.6 gigahertz away from a 20 megahertz line. Okay? So this is the data, same experiment, except the atom is prepared in the other state, and we see darkness, no photons, a little bit of shoulder here. So in a single shot, we just put a discriminator here, and we have a really, really good detector. More than 99%. In fact, more than 99.9%. And if we wanted another 9, we know how to do that. We don't have to, really. Only until we get a few thousand qubits do we have to go to that fourth 9. Okay, so that's the detection. So I hinted, why are we using ytterbium? This is actually the main reason, and it's an engineering reason. The reason is, to do coherent processing, we want to make a superposition. We actually use what's called a simulated Raman transition, a tool in atomic and solid-state optics a lot. We apply 2 laser beams whose beat note difference is nearly or precisely on this frequency here. And the good news about this laser is that this laser is so far detuned from the excited state that it doesn't scatter. So it's not measuring. It's doing coherent stuff. This is what we're going to make our quantum gates on. And the reason we choose ytterbium is there's a magic wavelength to do this, the kind of an optimum wavelength. In fact, I wouldn't call it the optimum wavelength, but there's sort of a local optimum where you want to work. And Rui Ozeri here in the audience knows way more than me about the scattering of photons and what's the best place to work. But ytterbium has a big fine structure splitting, 100 terahertz. And it turns out you want to tune about 1/3 of the way up to realize this sort of local nicety. And in ytterbium, that magic wavelength is this, 355. That's why we're using ytterbium. Why is 355 special? Because it's a commodity. That laser you can buy. You can buy as much power as you want. You can buy 100 megawatts of that power if you want. Of course, that's a national laboratory called the National Ignition Facility. at Livermore in the US. It's the third harmonic of YAG. It's just an industrial laser. It's used as a standard for lithography in the semiconductor industry. So we're actually leveraging semiconductors here, but in a very indirect way. This laser, when you buy it, it only has one adjustment, and it's the on button. This is why we're using ytterbium. I've spent most of my life, a lot of my life, inside lasers. I like it, it's fun, but no more. If you're going to build a quantum computer, you can't be spending time in a laser. So the laser that's important here to do gates is an industrial laser. You turn it on and it works for years. That's no lie. And it's really amazing. It's a beautiful type laser. There are many made every year, so there's lots of marketplace and so forth. It's a pulse laser, which is also nice. And in fact, the pulses have just the right time scales. It produces a frequency comb when you let a lot of pulses through. And basically, every tooth of that frequency comb and its neighbor, that's 12.6 gigahertz away, gets to drive this coherent transition, and they all add up coherently. That requires that this comb, that the mode lock laser be very passively stable, and it is. We're not limited by the coherence of that laser in anything we do. So we don't even have to generate the other tone. This laser produces both tones. So here's how it works to run gates between ions. Well, if we make this frequency difference between the comb teeth be exactly this frequency, then we're going to do NMR, basically. We're going to drive that single spin up and down and up and down. How do we entangle ions? Well, this is why we use ions, because they interact. So this is a very simple picture of how they get entangled. The physics is true here, but I'm cutting some corners to make it explainable, and I'll maybe talk about different cases. If we have a bunch of ions in a string and we want to entangle a couple of them, we're going to use their collective motion. I think of a bunch of pendulums connected by springs here. If you wiggle one of these ions in space, then they all know about it. And it's these vibrations that turn out to be the wiring, the effective wiring between the qubits. This is very neat because we don't have real wires. If we had real wires, it would be a solid-state system. This is not a solid-state system, so we have no man-made pieces here. Of course, the laser's man-made, and the laser has noise. But all of the noise, the entirety of the noise in our system is from the controls, not from the qubit itself. All right, here's how it works. If we want to entangle two ions, like the fourth one and the 18th one here, something like that, we shine laser beams on just those two ions. And without going into the details, this laser beam is actually an optical tweezer. It pushes the atoms. But it pushes them in a special way, depending on their qubit state. So for instance, it pushes the atom up if the atom is in the state up. So if the spin is in the state spin up, it pushes it up. If it's spin in the state spin down, it pushes it down. So what happens here is that if you look at these two spins, if they're both in the same state, they move up together or they move down together. In either case, their separation is exactly what it was. Their Coulomb energy is the same. But if they're in the state down up or up down, they get pushed apart a tiny bit. Well, that tiny bit turns out to be a lot in terms of Coulomb energy. If you calculate the defect in the Coulomb interaction, this turns out to be a pretty big number. And it's effectively a dipole-dipole coupling because we're making little electric dipoles here, so it makes sense. And the size of this effective dipole moment is huge, even bigger than molecules with electric dipole moments that are induced. So when you look at the four possible states of these two qubits, quantum mechanics says that if we have an energy shift, then the phase factor advances or gets retarded by that energy. And so I just told you, you get the same energy shift if you're in one of the two odd parity states, whereas the even parity states have no phase shift. This is a nonlinear operation because what happens to up is not a product of what happens to down and up down. It's nonlinear. And when that phase is, which is this energy shift times the time that they're displaced divided by h bar, when that phase is pi over 2, it's an important part of a universal gate, very similar to the controlled NOT gate, and it makes full entanglement. Okay? So you can see at a high level we're using the Coulomb interaction to entangle these. Now, two sleight of hands that made this very easy. One of them, actually, we don't do this in the z basis, where we're having spin up and spin down. We actually do it in the x basis, where the spin-dependent force works on up plus down and up minus down. But that's just a basis change in the Bloch sphere if you want. Our native interaction is called an Ising gate, or an XX gate, or a Molmer-Sorensen gate, whatever you want to call it. Molmer and Sorensen are the two who sort of were the first to put this on the map, following Serac and Zoller's seminal idea to use ions at all in a slightly different way. And so this is sort of our native gate, the Ising gate. Now, the other sleight of hand is that I didn't tell you about the normal modes of oscillation. They're typically a few megahertz, meaning that the period of oscillation it's faster than a microsecond. But these gates typically take tens or even hundreds of microseconds. So in fact, you can't just push one or two ions without all the others knowing about it. So there are normal modes of oscillation, and you have to take care of those. Now, if you have a lot of laser power, and you can do it really fast, you can move the ion and bring it back before a microsecond or so, before a few hundred nanoseconds, then this treatment is actually a good approximation. But in practice, we don't do that. We use lower power laser beams, so we have to deal with all these modes of motion. That's a classical problem. It's a classical complexity problem, and it turns out we can laser pulse shape these forces so that all the normal modes cancel at the end. I've brushed a lot under the rug. We have to pre-calculate classically what to do to our laser pulses depending on which ions we entangle. They all have their own personalities. The way again, you should think about these pendulums. How exactly would you move pendulums so that they talk to each other, but all the others at the end of the day don't notice it? Okay? So there's classical engineering involved there. So this is a sort of a schematic of one of our first, I would call systems. I'm a little embarrassed calling it a system. It was really a physics experiment. But we had individual addressing on only 5 qubits. We were hoping for more like 20, but our ion trap broke and one of the electrodes didn't work, and we could only hold, this is typical, and yeah, anyway. We could only hold a few. We're working with 7 or 8 ions in that system right now. But even though it was small, it was quite powerful because for the first time in my life, we were calibrating the system in the morning, and then all afternoon we were running algorithms on the PC next to the experiment. We didn't have to do optics. Of course, things would drift over the course of a few hours. But with this experiment, we finally got the notion of this quantum computer stack. From the bottom, all right, we have our ion trap, and we're hitting it with laser pulses, and we're doing the detection and so forth. A step up, we had to design the laser pulses. With 5 ions, there are 10 possible pairs. And so we had to make 10 calculations on what to do with the lasers. If we want to do a gate between 3 and 4, that's a particular laser shape for that gate, or 1 and 5 is different. Going up the stack, we're doing Ising gates. These XX gates, textbooks have controlled NOT gates, which is a different family. And so you need to translate between them. That's called a compiling step. When you do that, you can do it efficiently or not efficiently. And there's a black art in doing quantum compiling. And at the very high level, you have theorists that say, well, I'd love to do this algorithm, this game of 20 questions. That's called the Bernstein-Vazirani algorithm. I'd love to do that. Now, if you'd love to do that algorithm, you don't want to know anything about atomic physics. But you do need to somehow make a circuit out of C-naughts and then go all the way down. So this is something new in the field, and it's everything above here is not really atomic physics or even physics, I would say. Okay. So we typically draw gates or circuits like this in space and time, unlike classical computers. Here we have a bunch of qubits. We usually write them vertically and have rails. And this is a controlled NOT gate, sort of like the Ising gate I showed you between. And typically over time we operate some gates like this. So this is a quantum computer algorithm. And I show you this because there's just a kind of a 1-minute animation of what this system looks like. So this is an optical switch, 32 beams actually, and they're introduced to this chip. And we first initialize all the qubits with a resonant optical pumping beam, so they're all prepared in, say, the 0 state. Then we do, say, a gate between these two. Then we do a single rotation, which is just flipping that spin a certain amount depending on the circuit. Do a gate between those, do a gate between those, and you can, and so on and so forth, whatever the algorithm requires. And then at the end of the day, we make a measurement of all the qubits, and the ones that are bright are ones, the ones that are dark are zeros. That's it. That's what a quantum computation looks like in this system. Lots of optics. In fact, it's all optics. So when we built that 5-qubit system, we started doing things. Remarkably, we started getting approached by theorists and people across the world that wanted to run applications. And this was helped from the fact that this is 2016 or so. IBM had just put their first superconducting system online. They put it on the cloud. And this was amazing because people, I mean, 5 qubits is not amazing. 2 to the power 5 is not very big. However, their quantum computer was on the internet. People could use it. They had thousands of people signed up for it. Just that alone was interesting. You got people thinking about quantum gates and quantum circuits and so forth. Well, as it happens, right around that same summer, our system also had 5 qubits. It was just a coincidence that they were the same. And the people that were running their algorithms on the IBM quantum computer found that their algorithms pretty much petered out after 1 or 2 operations. It wasn't doing anything. It wasn't, it was working very poorly. Our system was working much better. Well, they're based on atoms. Of course they were working better. We didn't have a cloud service though. We had graduate students who would, talk on the phone, oh, that's what the circuit looks like, and spend a few months iterating what's the best way to run it and so forth. Okay, so it was very interesting though. It was just a pipeline of people from all kinds of different institutes, companies, government labs, universities, doing all these, these are all demonstrations involving small numbers of qubits. A few of them have lots of qubits. These are not universal quantum computations. They're simulations. I'm going to talk more about that tomorrow. But one of them, again, what I've loved in the last few years is it's like I'm in school again, learning about some weird model in magnetism, or learning about something, quantum scrambling, that I've found out is relevant to black holes. So that's one of my favorite examples. Let me talk about that. And again, I'm really on thin ice with this slide. Obviously borrowed it. But you may have heard about the holographic principle of general relativity and quantum gravity. And it relates to entanglement being a way that you can communicate through wormholes. It's all these buzzwords together makes my head spin. But the relation to black holes is that when you put half of an EPR pair, half of an entangled pair of qubits into a black hole, that half is thought to thermalize with the black hole and it scrambles. This is not just entanglement with every piece of the black hole, but it's infinite depth entanglement, depth as big as the system can see. So scrambling is a process that we're learning that's more than just entanglement, but it's deep entanglement. And the Hawking radiation of a black hole can be correlated with the qubit you kept, in some cases, to retain the information, kind of a surprise. And these connections are very deep. Juan Maldacena, John Preskill, Lenny Susskind, and others, Patrick Hayden have been thinking about these. And I was reminded of the saying ER is equal to EPR. The Einstein-Rosen bridge is related by EPR pairs. And I also understand there's a physical Einstein-Rosen bridge on this campus, or at least it's called that, fittingly. So the circuit I'm going to go quickly here. The circuit we're going to demonstrate here is a litmus test for scrambling. Scrambling is a property of a unitary process. And it's, I'll just write down the circuit here. It's a 7-qubit circuit. And the unitary we're interested in is this, U. You know, we have to implement its time reverse version as well. And in a sense, we're correlating the forward and backward evolution of U related to something called an OTOC, an out-of-time order correlator. That's sort of a hot topic these days in quantum information. But here we start with all of the qubits initialized except for the first qubit. It's prepared in some state. Doesn't matter. It should be a random state. We know what the state is, but it's some state. And this 3-qubit unitary, apologize for saying this, that represents our black hole and our reverse black hole, if you want. And the question is, does this U scramble or not? Well, it turns out, using this circuit, there's certain entanglements set up. 2 and 5 are entangled, 3 and 4 are entangled, 6 and 7 are entangled. You run this circuit, and then based on the measurement, the Bell measurement of appropriate pairs of these output qubits, if and only if U scrambles, the initial state is teleported to over here. And I can't prove this. It's pretty remarkable. Benny Yoshida and Norm Yao showed me this a couple of years ago. And more importantly, they said, here's a circuit. Can you do it? And so we started learning about how to implement this circuit. And for our unitary operator, you can't read this, but there's a parameter in this operator, a theta here, that we can vary between scrambling and not scrambling. And again, the teleportation aspect, the teleportation aspect comes from this, again, I don't like the term quantum teleportation so much, but it actually conveys the meaning here of the movement of information. Not matter, we're not moving Captain Kirk from the spaceship to the planet, but the information contained in, say, a single qubit being teleported. And teleportation, here's Asher Perez as one of the inventors of the teleportation protocol, along with Richard Josa, Bill Wooters, Charlie Bennett, Gilles Brassard, and Claude Crépeau. This is the observation. As we get more scrambling, we see indeed the teleportation grows. It doesn't go all the way to 100% because we had noise. This circuit is actually, even though it's only 7 qubits, it's fairly deep. It required lots of coherence in the gates. And so again, this is just an example of an application way outside of our space. It's almost beyond physics in a way. It has to do with cosmology. But I think this is really the interesting use case of quantum computers. We're going to use it to help elucidate ideas in all walks of physics and science. Lately, even the Google X team is starting to think about using exactly this type of a circuit with different input states. So I'm sort of running low on time. Tomorrow I'm going to talk about how we, instead of focusing individual beams on individual qubits to do gates, if we illuminate all of them all the time, we in a sense are able to enjoy an all-on-all icing model, and we can do certain manipulations to simulate magnetism in many forms. And there's been a slew of ideas here, from storing spin 1 in a chain and doing dynamics there, all kinds of fun things. One of the most fun experiments involved a simulation with over 50 qubits, learning something that we couldn't calculate before, because 2 to the 53 in this case, 53 qubits, 2 to the 53 is really big. And again, I'm going to skip over this because I don't have time to talk about that. I want to, again, I'll talk about the quantum simulation area tomorrow. But we are interested in building quantum computers out of this technology, but the real problem, if you visited an AMO lab, or any physics lab for that matter, but AMO is particularly pernicious, it's just ridiculous. I mean, this is a lab where we have a single ion in a vacuum chamber right here. But I mean, look at the real estate devoted to lasers, optics, everything is flexible, all the electronics and so forth. This is no way to build a system. It's not a system. This is a physics experiment. Now, the good news is if you know what you want to build, you don't have to make every single optical stage have 3 screws on it so you can adjust everything. It's a great way to learn, and this is what students are used to, and you can be flexible to do research. But if you want to build a system, you really need to nail down the design. And over the last many years, in a collaboration with Jungsang Kim at Duke University, and funded in large part by IARPA, which is the intelligence agency version of DARPA in the US, they're very interested in quantum computing for the factoring application I mentioned. Without much exaggeration, everything you see here, not the students, everything you see here is inside this box. It's about 1 meter cubed. All the important stuff, the laser that has the coherent interactions, all the beams. And we don't open that box. Everything is automated. And all the mounts that are important we have on automatic adjustments. And inside that box is one of these Sandia chips. And the workings of what's going on there, we have a template of 32 individual beams. They're each individually controlled with a multi-channel optical modulator. So we can do amplitude, phase, frequency modulation of each of these beams independently. And this is where a lot of the control technology goes. We have very fast and deep AWGs driven by FPGAs that drive these 200 megahertz signals to do so our quantum computer algorithm goes into here. All this other stuff is sort of housekeeping. it's lasers. And of course, things drift, and by making things small, the footprint small, the performance is a lot better. And if this looks like something that maybe companies should be doing instead of a university, this is, of course, the model behind what IonQ is based on. At IonQ, we've built 4 systems, and there's another 3 on the way this year. Pretty much inside the box, it looks pretty messy. It's the same thing that we have at the university. Here's systems 2 and 3. And to give you an idea of the automation that we have over there, and we have it almost as good at the university. This is a real video of loading exactly 24 ions, and we load them one at a time from here and shuttle them one at a time, a millimeter away, a couple millimeters away to the zone here. They have a little loading slot, which has a pretty high probability per load. Not every time loads. And as soon as we hit 24, the camera recognizes it. They're zigzagged. It's OK. We lengthen the axis and then refocus, ready to go. So that was real time. And this crystal can last, depending on anywhere between 15 minutes and a couple of hours. But we can load really fast. So this is a real system. You press a button, and that'll happen. And now you press another button, and you can execute an algorithm where the laser beams are going over the surface, like I mentioned. So at IonQ, we've been spending a lot of time over the last year not just building systems, but running them. Remember that game of 20 questions I said? That's the Bernstein-Vazirani algorithm. We've run that with any number of those 2 to the 20th possibilities. I guess it's actually 19 instead of 20. One of the qubits is actually used as an ancilla. So we're running fairly deep circuits as a benchmark. There's nothing interesting about this oracle. We knew what it was when we programmed it, so we're not gaining information. But it's a way to sort of test how the system works. We can run any of the 2 to the 19 oracles in that algorithm. On the molecule side, I mentioned water earlier. Water has only 10 electrons, but even still, with 10 electrons, we can calculate the ground state exactly. But we're running optimization algorithms to do that on our IonQ quantum systems. And one thing I failed to mention is that our systems are fully connected. We can run a gate between any pair of these ions. That's really powerful. We don't have to worry about just moving information around from nearest neighbor to nearest neighbor. And because these are ions, they sort of have the prerequisite for scaling. They're absolutely identical. That's not a problem to scale. And so sort of taking a page from classical computing, the way we're going to really scale up, we're not going to put 1 million ions in one monster string that would occupy 10 meters or something like that. We're going to make a modular system where we actually connect different modules of maybe 50 or 100 ions in each chip. And we can do this using photonics, actually. I didn't have time to talk much about photonics at all, but the idea is we can map a single qubit to a different species qubit that can emit a photon, and that can be entangled with another photon from another module and herald the production of entanglement. Again, I'm going way too fast here, but this is a very well-known Hong-Ou Mandel type experiment where we, by producing 2 photons at the same time, probabilistically, when they result in a certain correlation behind those detectors, these 2 atoms are entangled. And in ions, 13 years ago actually, it was first shown, this entanglement long distance. It's been reproduced in many other technologies. And the state of the art is actually, all right, this is a pretty slow speed, but it's actually much this is a pretty slow speed, but it's much faster than the decoherence from our classical noise sources, so it's still useful. So just about done here, kind of stepping out and now away from trapped ions. This is a picture I borrowed from my friend Hartmut Neven, who runs the Google experimental quantum team with John Martinez and so forth. What we're plotting here is the number of qubits you need to do, the number of qubits you need and the number of operations, the circuit depth, if you want, to do certain things interesting. If you want to factor numbers, again, these are pretty stratigraphic numbers here. We need millions of qubits, probably billions or more of gates, so that's really far away. This red line is important because it turns out if you're left of the red line, it's boring. If you're left of the red line, you can calculate it classically. So if you have a lot of qubits, you need to do a certain number of gates. If you have a lot of gates, you better have a certain number of qubits. So it's no fun to be over here or over here. You really need to be up and to the right. With ions, we're marching along that way, and these red dots haven't been demonstrated yet. It's convenient, right, because they're on the interesting side, but we have well-determined engineering paths to get there. A couple of the data points, these are non-universal systems. These are quantum simulators. I include them anyway. And these are sort of 2-qubit experiments with very high fidelity. And at IonQ, we're sort of right on the verge of that line right there. So things look very promising, I think, with this technology. I didn't talk about error correction at all, but to do error correction, you need to be up in that purple range just to get going. So error correction won't play a role in quantum computing for some time, despite what you've read. It's going to be many years before error correction is really relevant in this field. But it's possible that we can do things that don't need error correction. And this is also a culture change. People aren't used to that idea. But in atomic physics, we have the possibility of getting very high fidelities without any error correction. Okay, really stepping back now, I know Israel, like many countries across the world, are going strong in this field, forming initiatives. And it's well-founded because, as I like to say, universities where we're comfortable with the strange features of quantum physics, we don't build things. We don't build systems that third parties can use. That's not our role at a university. That's what industry should do. But the problem in industry is they don't have people that, some of these engineers don't even believe in quantum. They think it's sort of science fiction. So there's a big chasm between university and industry. We need both. And governments can historically play a role to help either in government labs or making, investing in that transfer. And so the US has passed our own version of the NQI Act, and being as an employee inside the Beltway, I'm not a federal employee, I work at the University of Maryland. I've played a big role in helping Congress understand this field and what it means and what they might think about doing. And indeed, this was passed last year, and it directs agencies to spend lots in this field, and I think this is being replicated across the world. We weren't first. I think the UK was probably first. China's putting in a lot of money into this field. The European Union, of course, with their flagship, is doing as well. This field at a very high level is generally split into these categories: computing, simulation, communication, and sensing. To me, they're sort of all one and the same. Sensing is a little different. It's much more in the present than in the future. But to do good sensing, you have to have really good measurements, and maybe you want to make entangled states for enhanced sensing. So there's quite a tie there. These two, I think, shouldn't be separated. If you want to make a big computer, you're going to be doing networking. If you want to make a long network, you're going to be doing computing at the individual repeater nodes. So they're going to be tied together. To me, they're really not different. Finally, my last slide. I borrowed this from the cover of Tech Review, MIT Technology Review. The title was actually AI and blockchain, I think. But it could have easily been quantum computing. There is a hell of a lot of hype in this field. Quantum computer is the new paradigm for computing. We don't know. My guess is it's going to be put to use for something that we don't know about now. I don't know how widespread it'll be, but it has great opportunities. And of course, the hope is something else. But there is an overlap, and I think there is a role for this field to play in the future. So I have a research group at the University of Maryland. I was CEO of IonQ for about a year, but I'm glad to kind of have stepped out of that role. It was by necessity I had to do that. But I am much more comfortable on the research side of things. If you're interested in the work, please contact me. Always interested in hiring really good people. This is an old picture from IonQ, which is in College Park, down the road from the university. We now have about 60 employees, actually. It should be updated, and it's funded by venture capital. Thanks for your attention.